Good morning, everybody. I don't want my picture, so I'm going to shut my picture down. Um, we're on chapter 23, which is inferences about means. So what we were doing in the previous chapter was doing inference, which is confidence intervals and hypothesis testing for proportions. So of course, the question yields itself is, if we're able to do it for proportions, can we also do it for means? And the answer is yes, of course we can. So the next few chapters are going to be about doing inferences for means. One sample and two sample, and we're going to be looking at it a little bit differently from the means perspective because there's a little bit of nuances that are different. There's actually one major nuance that is different. It's called a t-score instead of a z-score, and you might have done this in algebra too. So what this slide is telling us is that, sorry, let me go down here, is that the central limit theorem told us that the sampling distribution model for means is normal, right? Unimodal, symmetric, with a mean mu and a standard deviation of the standard deviation divided by the square root of n. Okay, so what's different about means than proportions, I thought we were going to talk about it right now. Oh, is that proportions are linked their standard deviation to the proportion itself, because the standard deviation equation is the square root of the success proportion times the failure proportion divided by n. In the case of means, the standard deviation is not linked whatsoever to the mean. So instead, we use the standard deviation over the square root of n, or most of the time, there is no population standard deviation because we just did a sample. So we have to use the standard error, which is going to be small s divided by the square root of n. Okay. So this question they are giving us is, based on weighing thousands of animals, the American Angus Association reports that mature Angus cows have a mean weight of 1,309 pounds with a standard deviation of 157 pounds. This result was based on a very large sample of animals from many breeds over 15 years. Okay, so they're kind of telling us this is, large sample. We don't have to worry about any sort of issues at all. Let's assume that these summaries are the population parameter and that the distribution of weights was unimodal and reasonably symmetric. What does the CLT predict about the mean weight seen in random samples of 100 mature Angus cows? Now, if you notice, they're not telling us exactly what to do, but this prediction is making me think that I'm going to create the 68, 95, 99.7 curve. Okay, so let's see what we can do here. So we have that. We have our mean cow, which is 1,309, and we're going to do 68. We're going to do 95, and we're going to do 99.9. So how are we going to do that? We're going to find this standard deviation. How do I do that? I'm going to do the standard error equals, well, I guess this is actually standard deviation because it's over a large time period. We have 157 divided by 100 mature cows, so it's going to be the square root of 100. So when we do our math, 157 divided by 10 is going to be 15.7. So the standard deviation, I'm pressing on something, so it's making all these noises. Sorry. So we're going to have, okay, is it good now? Oh boy. Okay, so the standard deviation is going to be 15.7. What do we do that information? I'm going to add it. Stop. Thank you. We have 1309 plus that, 1309 plus 13. So we have 1324.7 plus another, which is going to be 1340.4. And finally, we have 99.7 plus 15.7, which is going to be 135.6.1. Now we're going to go backwards, minus, and we get 1293.3, we have 1277.6, and we have 1261.9. So what is it telling us? We can then summarize that 68% of cow weights will be between 1293 and 1345 pounds. We can say the same thing, that 95%, blah, 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 is between 1277, 1278, and 1340, and we have 99.7%, blah, 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 is between, what is it between? It's between 1262 and 1356 pounds. Okay, fine. So now let's go through a little bit more about what's happening here. So we have extra variation in our standard error from S, the sample standard deviation. Because we're dealing with the sample instead of the population, will be extra variation. Here's the interesting thing about doing means. They're going to need to allow for the extra variation so it doesn't mess up our margin of error and it doesn't mess up our p-value, especially for small samples. The shape of the sampling model changes. The model is no longer normal. So what's the sampling model? It is called the Gossett's T, or what we call the T model instead of a Z. Okay, so this guy named William Gossett was employed by Guinness, the brewery in Dublin. And as you can imagine, they can't do too much sampling at Guinness or any other alcohol place because they will get inebriated very quickly. So they had to create this sample T model to be able to take very small samples and say, okay, this batch is good. Especially when we were talking about when he was around, which I believe was, a couple hundred years ago. I'm sure it says it somewhere in the book. I'm looking to see if it does. It doesn't matter. Anyhow, so he created this T model. Now, the main thing about T models that is very different from Z is that we have these things called degrees of freedom. A degree of freedom is super duper easy to know. A degree of freedom is just going to be n minus 1, the number in our sample minus 1. And this number will actually give us a critical value that is different from a Z critical value, and it'll be a T critical value. Okay, so let's see whether we can take a look at that for a minute. I have it right here. This is in the back of your book. It's also on that sheet of paper that you guys have been having. Forgive me, I think it is salmon. If it's not salmon, it's yellow. So we've been dealing with the Z scores, but if you take a look, you're going to have another section, which is going to be T. Let me see how it looks here. It says, yeah. Now, I believe your sheet, the yellow sheet, looks a little different than the book. So let me just explain to you what's happening here. In the book, they're giving us the two-tail and one-tail. In the case of, obviously, a confidence interval, we're going to be dealing with two-tail, super important. I'll talk about that in a minute. And when we're dealing with one-tail, that's when, obviously, we're going to be looking at something greater than or less than. Why is that important? Because on the book, anyway, they're going to actually give us, if we're looking for a 95% confidence interval, for example, for a two-tailed probability, that means that each side is going to be 0.025. So we would be looking at this column, right here in the middle to then look at our data. Now, how are we going to use the degrees of freedom? We're going to be looking down. So for example, in the case of the 100 cows that we just looked at, if we were going to be doing a ultimately doing inference, a confidence interval or a test, we would then use the degree of freedom to go down to 100 and do 100 minus 1. Now on this page, they actually don't have 100 minus 1, 99. So you're going to estimate that for a 95% confidence interval for 100 cows, which would really be in degrees of freedom 99, we'd be at this number right here. Now, is that a big deal being off? Well, look at between 100 and 120. It only went up by 0.00, down by 0.004. So you can imagine just going down 1 degree of freedom, one number, it might not even move. It still might be 1.984. I'll show you how to use the calculator for that in a minute. But using the page, again, now I can't remember. I don't have the sheets. I apologize, in front of me, and I'll look for it tomorrow, whether your sheet does one-tailed or two-tailed. But take a look, if you can, on your sheets. Go down to 95 degrees of freedom, 95% confidence interval, and go to 100 degrees of freedom, and tell me if it says 1.984. That's the number you're going to use for confidence intervals for certain. That's two tails. And then certainly once we start moving forward, when we're doing tests, you'll need to determine whether you use one tail or two tails. That being said, let's continue with the information. So what do we have here? When we're going to be doing a standardized t-score instead of a z-score, it's going to be virtually the same equation. We have t equals y bar. The y in this case is going to be our sample minus mu. That's going to be the expected value, divided by the standard error. And it could be standard deviation if we happen to have the information, which sometimes we do. Most of the time we do not. So, and then of course it says we estimate it, okay? And degrees of freedom, they're reiterating for us, that is n minus 1. So when Gossett corrected the model for the extra uncertainty, the margin of error actually got bigger. Your confidence interval will be just a bit wider, and your p-values will be just a bit larger than they were in the normal model. Just so you know, when our numbers start getting closer and closer to infinity, meaning large numbers in the sample, it's going to get closer and closer to a z-score. So the z-score and the t-score actually become the same with larger and larger samples. So obviously we don't have an infinity sample, but when it starts getting larger, 1,000, 10,000, they almost become one. So we're going to use the t model for means. We're going to use the z model for proportions. Super important. Put that into your memory bank, because as soon as I see means, I'm going to do a t sample. As soon as I see a proportion, I'm going to do a z-score. Okay? All right. So what is we just looked at finding the t-score. What does a one sample t interval look like? It looks just like the confidence interval we did for proportions. So let's talk about this here for a minute. We have here our sample. This is going to be the sample average. This is going to be the critical value we're going to find from either the sheet, the formula sheet, not the formula sheet, the table sheet, I guess I'd call it, or from the calculator, right? Times the standard error. And again, we know the standard error. The critical value, t star and minus 1 depends on the particular confidence level, C, that you specify, and the degrees of freedom in the sample size. So let's go through a problem, and that will show us how to do it manually as well as using the calculator. So we have this thing of fish, farm fish. Fish from many sources were analyzed for 14 organic contaminants. The study expressed concerns about the level of contaminants found. One of those was insecticide Mirex, which has been shown to be carcinogenic and is suspected to be toxic to the liver, kidneys, and endocrine system. One farm in particular produced salmon with very high levels of Mirex. After those outliers were removed, summaries of the Mirex connotations, parts per million, so it's like not a whole lot, were shown below. What does a 95% confidence interval say about the Mirex? And again, I have no idea how much Mirex there can be in salmon or for it to be bad for humans, but this is what's telling us. So let's first talk about a confidence interval. If we did it manually, my y bar is going to be 0.0913. My standard error is going to be the standard deviation of the sample, divided by the square root of the number in the sample. So let me just do that math real quick. 0.0495 divided by the square root of 150, and we get 0.004. So if I did this manually, I'd have 0.0913 plus or minus, we have to find the critical value, we'll find that in one moment, times 0.004. So let's find that here. So first of all, let's go to our sheet, and we'll look for that. So we're looking for a 95% confidence interval. So a 95% confidence interval. So our degrees of freedom would be 150 minus 1, which would be 149. It's not on the sheet. 150 isn't even on the sheet. But let's go down to 95% confidence, and let's see what we have. We have 140 and we have 180. Certainly 149 is closer to 140, so I'm going to use 1.977, okay? And that's going to be the number we would use in our formula. Oops, okay, here we go. So I'm going to write in here 1.977. How do I use the calculator for this? This is how we would do it. Again, you have to remember, that we are going to do a two-sided sample with a confidence interval. So therefore, it's not really 0.95, it's going to be 0.975 because we're looking to get it from both sides. So what I'm going to do is I'm going to go to second distribution, and we have, on everyone's calculator, you should have inverse t. That's going to allow me to put in my area, which is 0.975. My degrees of freedom is going to be 150 minus 1, which is 149, and I'm going to hit paste. Okay, and I'm going to hit enter. And the critical value I get is 1.976, which is close enough for what we just found, which was the 977. So either one would be fine. So when I do my math, I get, might as well do it here, right? So let's do, boop, boop, boop. I need both sides. I'm going to do 0.0915. I'll use from the sheet, okay? It doesn't matter. The numbers are going to be practically the same if I did it with them. And then we'll see what the calculator says when we use the function on the calculator. Enter. So I get 0.099. And then I'm going to go back here, and I'm going to go up because my calculator lets me do that. And I'm going to change it to minus. .083. Okay, so what does the 95% confidence interval say about Myrex? We are 95% confident that the true mean number of Myrex in salmon is between 0.083 and 0.099 parts per million. Now, a few things I just want to mention real quick. This is a decimal. Most of the time, we're not going to have a decimal. For instance, we're talking about driving speeds on the turnpike. It's going to be 67, the number, not a decimal. So just be careful, because this is not a percentage. This is actually a mean number, because this is parts per million. So this is a little bit of a weird one because it's a decimal to begin with. So don't let it confuse you. This is a proportion. It's not a proportion. Read in context. Real quick, let me show you how to use the calculator for this. We're going to go to stat. We're going to go to tests, and we're going to choose a t-interval. Okay. Enter. I'm going to choose stats for mine. And I'm going to put in, why is it blinking at me like that? Okay, so my X bar is going to be my 0.0913. My standard deviation, if you recall, was, what was it? 0.0495. My number was 150, and it's going to do a C level of 150, and I can leave it like that because the calculator is going to know that it is a two-sided. And sure enough, we got the same numbers. Okay. Have a great day, and we will continue with this doing assumptions and conditions, etc. tomorrow. Have a good day, everybody.